In this video, we're going to have a look at further integration of trig functions, but ones that look like this. Now, we looked at an earlier video in what happens if we have a composite function that's a power, and we can see that it's been multiplied by the derivative of the base function. Remember, we just add 1 to the exponent of the function and divide by that number so that we can undo it using the chain rule. Let's have a look at our first example. I'm just going to make sure that I have my table handy, which I advise you do too as you work through these. So let's have a look at this one. I want to see if I can identify a function and a derivative. Well, if I take cos x all cubed as my function, and I look, can I see the derivative of cos x? It is negative sine x. I've almost got it. So if I saw a negative sine x there, I know it would fit the rule. And we know that we can just create that situation as long as we do it in a mathematically legitimate way. So I want to see the derivative negative sine x, and then my function is cos x all cubed. Often it's easier to write a composite function like that so that we can see. Now, I introduced a negative. Make sure that you compensate with another negative. So let's see, there's my function. And there's my derivative. Cool, so it fits the pattern. I just need to take my function, add 1 to the exponent. There's my negative from outside. So I've got cos x to the power of 3. I add 1, I get 4, so it's cos 4 to the power of x. Then I divide by 4 and add my constant of integration. Let's just check that if I in fact differentiate this function, I'm going to get back there. If I differentiate this function, I've got something to the power of 4. 4 comes to the front, cancels with that 4, and I'm left with a 3. So that's cos cubed x. Then I go inside. My inside function is cos x. The derivative of cos x is negative sine x. The negatives cancel, and that's how I land up with my sine x. All right, let's have a look at this example. Now, it's quite interesting because this example can actually be done in 2 different ways. Just move the table down. So I'm going to show you both ways to do this. Right. So let's have a look first. If I can, so let's just see two ways. I'll just split it down the middle. So I'm just going to rewrite my function here. So I can just show you 2 ways to approach this. Alright, so if I look at my original question, can I immediately see a function and its derivative? Well, if tan x is my function, can I see its derivative? Can I find sec squared x? Yes. So I immediately can see that this is my function and that this is my derivative. Cool. So it fits the pattern. I then just have to add 1 to tan x to the exponent. At the moment it's exponent 1, so it becomes 2. So it becomes tan squared x divided by 2 plus my constant of integration. Awesome. Okay, now let's just check if we differentiate that. Do we land back here? Well, the derivative, let's first look at the power. Tan x to the power of 2. 2 comes to the front, cancels with that 2. I minus 1, so I get tan x to the power of 1. There's my tan x. I go inside. My inside function is tan x. The derivative of tan x is sec squared x. Awesome. But now you may be thinking, hang on a second, what happens if I didn't pick that as my function? Because what happens if you saw your function as sec x? So if you wrote, you can rewrite it like this. Your original, do you agree? You can rewrite as sec x times by tan x times by sec x. Still the same thing? Still got my sec squared x, I've still got my tan x. The reason why you might do this is to see your sec x as your function. What's the derivative of sec x? It's sec x times tan x. So in which case, there's your derivative. Alright, so if you did that, then you would have to add 1 to that function. So I'd get sec squared x divided by 2 plus my constant of integration. If you have to go and actually plot these graphs, you see that they're so similar. So you'll see that the integral gives you sec squared x over 2 or tan squared x over 2. But let's just test this one. Sec squared x over 2, my exponent is 2. The 2 comes to the front. When I differentiate, the 2's cancel. Then I see, all right, I've got my sec x to the power of 1. Then I go inside and I differentiate sec x, which gives me sec x tan x. Times those guys together and I'm all the way back here.